Today we're very happy to have Edwin León Cardenal from CIMAT CONACYT, who is going to tell us about real zeta functions and some problems in the study of oscillatory integrals. Whenever you're ready.
Okay, thank you everyone. Thanks to Imon, to Jack and Luis for inviting me to these conferences. This series of conferences they're very nice, and I'm very honored to be speaking here. Okay, so let's start. So the topic will be real zeta functions and some problems in the study of oscillatory integrals. So what we want to be studying in this presentation is the topic of oscillatory integrals. This is an approach for people that are not so familiar with the tools in analysis. And then I will talk about local zeta functions. Maybe this is more near to the topic of the seminar. So let's start. So what is an oscillatory integral? An oscillatory integral is something like the thing that you can see here is the integral over Rn of the exponential function. And here are some parameters. I is minus the square root of -1. Tau is a real parameter. F is called the phase. In analysis, it's called the phase function. And we can assume that it's a polynomial on the reals. But more generally, more generally, this is an analytic function, okay? And the other function, this phi, is called the amplitude, and it may be a smooth function, but most of the times is a smooth function with compact support, something that we denote right here, okay? These smooth functions with compact support are also called BAM functions. And this is the typical example of a BAM functions. This is the exponential of this function, of this function here, and this is the indicator function, okay? So there is some history that I'm going to tell you. These oscillatory integrals can be traced back to the original work of Airy, Stokes, Lipschitz, and Riemann, and so many other people. And there are very nice historic remarks in the book by Stein, Harmonic Analysis. Okay, you can see a lot of things there. So there are generalizations of the classical Fourier transform. So for those who don't remember what is the Fourier transform, here you have the definition of the Fourier transform in one-dimensional R. So phi hat is the integral of the exponential a minus I cx phi of x. So this topic is really important in harmonic analysis, in partial differential equations, probability theory, and number theory, among other things. In physics, they are used to describe problems related to shortwave oscillations. Some problems coming from optics, acoustics, quantum mechanics, and so on. And the main thing here is what is called the stationary phase principle. By a stationary point, we will mean a critical point, okay? But this is the language that the people use in analysis. So the stationary phase principle says that the main contribution in the asymptotics of oscillatory integrals, I want to talk, I will talk about what is the asymptotics of oscillatory integrals. But the stationary principle says that this contribution is given by the neighborhoods of the critical points of the phase. And the connection with singularity theory is that, well, this is critical points, okay? So at some point we need to use some algebraic methods to study these asymptotics. For instance, resolution of singularities. So there are two problems related with the study of oscillatory integrals. Two main problems, let's say. So the first problem is estimation, and for this problem, the idea is that once you have you have your integral here, and you want to bound your integral, and hopefully you can find a bound depending on the parameter to some power, okay? And this bound will include a bound that depends on several factors. In this particular example, it depends of the phase, of the amplitude, and of the constant n. Okay, but this is just an example of this type of problems. This will not be the main interest in this talk. We're more concerned with the asymptotics of these integrals. And here, the idea is to find some functions or family of functions such that the integral is bounded above and below by some family of functions, and this is dependent of some parameters. Okay, I will explain in the next slide what is this notation. Okay. So in asymptotics, in asymptotic analysis, what we have is that some I is bounded by G, or we will use also this notation, this I is O of G, to denote an estimate of this form. I is less or equal to a constant times the function J, okay? And we will use this notation to denote the fact that these functions or family of functions appears as upper bounds and lower bounds. Okay. Sometimes with when there is a list of parameters, we will use this notation. Okay. So the idea is that we have something like right here. Oh, sorry, I don't know what's going on. Okay. So the idea is more or less the following. If you have some function here, you can find a family of functions, let's say the red ones, such that the thing that you want to bound is above a family of these functions up to some constants. Okay, so it's something like this. So the first example is a very well-known example from calculus. I don't know, but sure, in analysis, you maybe in the classes that you teach, you have to show this formula or something similar to this. So when we have an integral of the exponential function to the minus alpha x squared, this is equal to the square of pi squared alpha. Okay. So this is not an asymptotic at all. This is an equality, so it's like cheating a little bit, but it makes my point. But the thing that I want to know is this power of the is this power of the parameter here. Okay, this is the thing that I want to highlight. So again, the principle of non-stationary phase formula, the one-dimensional case, says that if you have an integral, like this integral, remember that this integral is I to the minus I tau f, and then the function phi. So if you suppose that the function f is smooth and f prime is non-zero on the support of 5, then you can find these asymptotics. So there is a bound, or there is a family of bounds given by the negative powers of the parameter. Okay, and this is the type of things that we want to understand. So in several variables, the thing is more or less the same. So in this case, you need to ask that the gradient of the function is non-zero on the support of 5, and then you can find the asymptotics, and this is the constant here depend on the several parameters. Okay, but this is the easy case. Okay, what is behind this? Behind this, there is a theorem in analysis saying the following, saying the theorem is called the Riemann-Leibniz lemma. And this lemma says that if the phase has no stationary points, then the integral goes to 0 as tau, as the parameters, goes to infinity, faster than any power of t to the minus 1. Okay, so intuitively, this lemma says that if you have a function that is oscillating a lot, the integral the oscillations are increasing, so the integral, the net result will be 0. Okay, so there is some heuristics here. The thing is that these things that are called plane waves are putting one upon another, and the infinite superposition of these plane waves make that the total contribution cancel each other out. Okay, so for that reason, one expects that these things decrease in a nice way. Okay, so the net result of this superposition is a very small quantity. Okay, so another way to read the Riemann-Leibniz lemma allows us to say that the integral has no trivial asymptotics when the parameter goes to infinity, only when f has stationary points. Okay, and of course, if if we assume that the gradient of the function vanishes, there will be some issues. And for instance, in the asymptotic expansions, there will be not just terms negative powers of the parameter, but also there will appear some factors of log tau. Okay, we will see this during the presentation. Okay. So when the stationary set is no longer a set of isolated points, the asymptotic expansions are not fully understood in general. And you will need to use a resolution of singularities at the very least. Okay, so let's go back to the original problem, and we will try to see some tools to analyze the critical points of the function f inside the support of phi. So remember that the integral that we want to study is this one. And for this point, I'm going to assume that f is a polynomial in several variables, okay? Which has an isolated point. So the trick that I'm going to explain is the following. It's called the Galvanic trick, or the Galvanic form. So the thing is that inside this integral we have this f, and I would like to have this f replaced by the constant, let's say t. Okay. So if inside this integral I can make this to appear as a function, then the factor that I will obtain here is something like ai tau t, but t is a constant. So this will not affect the behavior of the asymptotic behavior of the integral. So this will be very, very nice if we can make to make this happen. Okay. What do we need to make something like that? Well, I'm going to use the following thing. I'm going to suppose that the support of phi is small enough such that in the region we can make this change of variables. Okay, and this is okay because this change of variables is guaranteed by the implicit function theory. So this trick amounts to use this change of variables. Remember that t is different from 0. And then what we are left is something very strange here, something that I'm going to denote by this function j of t. And we are splitting this integral into negative t and positive t, okay? So I'm going to explain better this factor that appears here. But this trick let us with something in one variable, okay? So this integral is separated in two integrals, but they are just integrals in one variable, okay? So I'm going to explain what is the meaning of these things, okay? These functions are called the Galvanic functions, okay? So what is behind this thing is the definition of the Gelfand form. So you have a smooth function from Rn to R and a smooth differential in form omega that exists in smooth differential n-1 form phi c such that this equation here holds. Okay. Here is an example. If you consider this polynomial, then you need to find a form phi c satisfying this relation, and you can look at it just by the very definition. You need to compute the differential of f, and then look for some function of this form. This should be something, in this case, in just one variable, it would be something like some function, let's say j, depending on x and y, and then dx, and then the result should be dx dy. Okay, so when you solve this equation, what you found is that g should be -1/2y. Okay.
So excuse me, can I ask something? So in the definition, is it really deep psi or should be just psi? Because deep psi is an n form. So
no, psi should be an n-1 form.
that's right. So if you take deep psi, this would be an n form. So with the df, it will be a.
No, here we are on two variables, so you need to consider. Okay, maybe this x is wrong. Are you saying so?
I think I'm complaining that in the definition, if you take, so if psi is an n-1 form, if you really have deep psi here, this would be an n form, and then with the df, wedging with the df is an n+1 form. Maybe I'm missing something. So I was asking whether it's really deep psi or you just want to have psi.
Yeah, maybe it's just psi. Okay, yeah.
Thank you.
Sure. Yeah, sorry, this, yeah. Okay, so let's continue. So this lemma says that this is always possible. So you can make this assumption that I wrote in the previous slide. So you can turn this integral into a one-dimensional integral of this form. So f is equal to t, and inside this integral is the Gelfand form, and outside the integral is the function where t is constant, and you are integrating over t. Okay, so this justifies the change that I made in the previous slide. Okay, so how is that this thing can help us to solve the problem of asymptotics? So the key idea is the following. So this is the equation that I wrote a couple of slides ago. So you have these functions g minus and g plus. So the idea is to reduce the study of these asymptotics to the study of asymptotics of these functions, but these functions the asymptotic of these functions is when the parameter t goes to 0, okay? And this is something that I want to explain later, okay? But the key idea is to reduce the problem to the problem of just one-dimensional integrals. And then if we can determine in some way the behavior of the asymptotic behavior of these guys, then we can say something about the original integral, okay? This is the strategy. So let's consider an example that is like something that you can expect very easy. So we have monomials in several variables. The function f here is this monomial here. And the differential form omega is the whole of this thing. Okay. So you can construct actually the Gelfand-Leray form by making some calculation. For instance, by induction is the best way to do this. And you can prove that this function j is smooth and is equal to 0 outside a sufficiently large interval, okay? So what Jean Quartier proves in the 70s is the following, is that these integrals, actually this should be g plus, g plus. This integral has an asymptotic when t goes to 0, and in these asymptotics, what appears is a double sum. I will, but the terms that appear here are powers of t and powers of. Sorry. Okay, let's continue. So there appear some powers of t and some powers of the natural logarithm of t, okay? So what I'm not saying here is where these guys alpha comes from. So in this slide, I just say that this alpha runs through some discrete subset of R bounded from below. And why is that? Because I want to make the connection with another object that is the local zeta functions, okay? So in this connection, I want to interpret these A guys and the alphas in terms of Laurent coefficients and poles of another object of local zeta functions, of real zeta functions, okay? What is a zeta function? A zeta function is something like this. Is in this case, you have a polynomial f, and then you raise this polynomial to some power sigma, where sigma is a complex number with sufficiently large real part, and omega is a form which has complex support. So I want to explain this theorem of Jean Quartier in terms of the poles and Laurent coefficients of local zeta functions, okay?
Sorry, can I ask a question? So this theorem of, oh, sorry, I forgot the name. Like
Jean Quartier.
Jean Quartier. Is this still in the monomial example or?
Mm-hmm.
Okay, so all of this is
Yeah,
in
yeah,
the
yeah.
monomial example.
Yeah, this is the whole thing in the monomial example. At the end, well, later I will try to explain the general case. Okay.
That's great. Thank you.
But this is in the monomial example case. Okay. So what is the set function of a monomial? So I'm going to consider is exactly the same things that were before this monomial here, and this is one the thing that I was calling omega. Okay, this was my form omega. Okay, so this result says that this function defines a holomorphic function as I'm considering this as a function of the parameter sigma. Okay, so here they define a function, let's say, of sigma, that is a complex number, away, and this function will be holomorphic away from the points belonging to the following arithmetic progressions. Okay, so the thing is that what appears here is the power of the m1 is the power of this guy here, and then in the denominator what appears is the power of the function. Okay, and moreover, at the point belonging to exactly r of these progressions, the function, the zeta functions of this monomial, they will have poles of order bounded by r. Okay. Okay, so I'm going to make a proof of this. Well, actually, it's a cheap proof because I'm going to prove just the simple one-dimensional case. So let's consider this function. This is the integral. I was using the notation f minus plus f greater than 0. I'm just here. I'm just simplifying and writing the positive part and taking this definition. So the first thing that we know here is that this function is finite when the real part of the parameter sigma is greater than minus m mass plus 1 over k. And how's that? Is because this is less or equal than the integral of the norm of the things that is here, what appears here, is the real part of k sigma plus m. 5 and the x. Okay, and this is okay. This is a continuous function because you know this. One may think that the problem is that this integral will have problems at the infinity, but then you remember that this function has complex support, so this integral is actually happening on a compact set. Okay, so on this compact set, this function will be well defined when the real part of this function is greater than minus 1. Okay, and this is exactly this notation here. Okay, so okay, so let me make this another extra drawing. So we have 0 here, and we have minus m plus 1 over k here. Okay, and this first quality says that my function as a complex function is defined over this set, okay? So the first thing that I'm going to make is call this integral I, just for lack of imagination, and I'm going to separate this integral in the following way. I'm going to consider the integral between 0 and 1, and then the integral between 1 and infinity. The thing is that this integral, this part, has no problems, because actually we can use the same argument to say that this integration is happening on a compact set, so there is no possible problems for the convergence of this integral. Okay, the problem is here that if x is 0, this may be problematic. Okay, in this integral. So I will focus on this first integral, and I'm going to separate this integral in the following way. I'm going to add and subtract phi of 0. So this first integral, this first step is okay, and we note and from this step, from this one to this one, what happens is that I'm making the integration of this guy, okay? And this is something that we can show that is perfectly fine. We can make this integration like in the usual sense, and evaluating, you get this term, okay, here. So what happened is that this first term has the following characteristic. Remember that this function phi of x, when we consider the Taylor expansion of this function, the thing is that phi of x, this guy here, is equal to x times some phi tilde of x, and this phi tilde of x is again a C infinity function with compact support. Okay, this is just because I'm looking at the Taylor expansion. Okay, so what happened is that in this first integral, when I have it is x to k sigma plus m plus 1 multiplied by phi tilde. So this first integral is defined when the real part of sigma is greater than minus n plus 2 over k. Okay? Now, this second term is well defined when sigma is different from n minus n plus 1 over k. Okay? And this is well defined for any sigma. But this is an equality, okay? This is an equality of I. Oh, sorry. So this is an equality of I. So this function that was originally defined in this set now is defined in a bigger set. Okay? What is this bigger set? Something of this form. is 0. Here is, sorry. Here is minus m plus 2 over k. And there is a problem here in minus m plus 1 over k. Okay? So this set well, that should be a blank point here. Okay. So what we have, what we make with this computation is to extend the definition, the original definition of my integral to the left. Okay. You can iterate this process.
I just want to make sure I understand. So in the previous, so sigma is a complex number, right? So
yeah.
So sigma is, how to say, what are the values allowed in the y-axis? Everything except at that point, right? So, is that right?
Yeah, is that right?
Okay, thank you.
Yeah, yeah. Yeah, thanks for the question. Okay, so we can iterate this process, and by iterating this process, I mean this integral, this let's say, let's use another color. This integral here is the integral of x to k sigma plus n plus 1 times a function phi tilde. Okay, that is again a function of the same form. So you can repeat the same thing and do something like this, but with phi tilde. Okay, and you can do that again and again and again. And after L steps of this way, what you have is this function f, this original monomial, and then another function phi, let's say double prime or something like that, and then the result of the computation of several of these integrals that you, when you add phi 0, phi tilde of 0, and so on. So what you get is this thing, and this is just the Taylor theorems and the Taylor terms. And what happened here is that this function has a power of this function phi double prime is some power of x to the L, and you have these guys here appearing in the denominator. So what you get, something like this in the same. So here is 0. There is a blank spot here. That is minus m plus 1 over k minus m plus 2 over k. And there is a lot of these guys here. And you have here minus m plus L over k. Okay. So your function is well defined over these guys. Okay. So remember that I'm going to go back, because our theorem was saying that our function is well defined away those guys that I just described in the previous slide in the one-dimensional case. Okay, in the one-dimensional case, you have just one of these expressions, but in the several in several variables, they appear one for each monomial. Okay. And what we prove is that these guys, they are possible poles, and the order of these poles depends on the matchings of these things in several of these arithmetic progressions. Okay. Okay. So let's finish the business that we were dealing at the beginning. That was the estimation of the oscillatory integral for a monomial. So Bartchenko proves the following: the integral with the monomials, the thing that Jean Quartier proved at the beginning, this is the monomial here and the other monomial here. This integral has an asymptotic expansion of the following form. This is again the same thing. What appears here is the parameter of t is the power of the parameter tau, and then the power then some powers of the logarithm of tau. But the alphas here are running through the sets of the possible poles of the local zeta functions that we just compute, these guys. Okay. So this is the first thing that we can describe these alphas in terms of these arithmetic progressions coming from the poles of the local zeta functions. And what about the coefficients AI? Actually, these coefficients are called distributions, okay, because they depend on the function phi, but they depend in a special way, okay? They are distributions depending on the amplitude, okay? If you don't know what a distribution is, don't worry, but this is the technical thing, and this is very, very interesting. Moreover, these distributions are given as or they can be computed as the Laurent. These guys are given as the Laurent. They are given as the coefficients of the poles in the Laurent expansion, okay, of the local zeta function. So what is nice about this presentation of this theorem is that it links to objects. One is the oscillatory integrals that appear here. They were the first things that we study, and it links this object with another object that is the local zeta function. Okay. Okay, but this is the story just for the okay. What is the content of this slide? This formula says that the trick that we used at the beginning was saying that we need to study the asymptotic expansion at infinity when the parameter goes to infinity. And this is somehow related with the asymptotic expansion of some function j when the parameters goes to 0. And the relation is very subtle, and it depends on the Fourier transforms and some properties of the Fourier transform of these guys. I'm not going in the details, but you can check this strategy, for instance, in the book by Arnold Borchenko. Okay. So what I'm skipping is, because I want to discuss in more detail this, but let's finish this topic about oscillatory integrals. So a local zeta function, the general local zeta function, is something like this. It's an integral of the absolute power, absolute value of the function f. This function can be a polynomial, but also an analytic function, raised to the power sigma, and then you multiply by a function phi. Okay. So this is well defined when the real part of the parameter is greater than 0, and moreover it defines a holomorphic function there. So the first theorem about these guys is the theorem that was proved by Gelfand and independently by Atiyah, saying that this function admits meromorphic continuation to the whole complex plane. And moreover, if you consider a given resolution of singularities, and these are the numerical data of the resolution of singularities, then the candidate poles, we have this form. Okay, they are given by this arithmetic progressions, where the data here is the data and the numerical data of the resolution. So how is this related with the problem of asymptotic estimation of oscillatory integrals? Well, here's the general theorem on oscillatory integrals. So recall that our oscillatory integrals they are this type of objects, and we are going to suppose that, to assume that f is an analytic function in a neighborhood of its critical point. We also need to assume that in this critical point the function f is equal to 0, and then the support of phi of the amplitude is concentrated in a sufficiently small neighborhood of C. In that case, we can prove that this integral admits an asymptotic expansion of this form. This is exactly the same that Barchenko or Jean Quartier put. But then what happened is that in this case, again, the coefficients are distributions. Again, we can read these distributions as the coefficients of the poles of the Laurent expansion of the local zeta functions around the poles, and this alpha now runs through the arithmetic progressions of these through these arithmetic progressions given by the data of the resolution of the singularities. So this was the whole point of the first question. So in order to know the asymptotic behavior of a general integral like this, we need to use resolution of singularities, and we need to use, well, we choose to use local zeta functions in order to describe better these guys. We choose to use local zeta functions in order to describe better the AIs and the alphas. But the thing is that if you want to know the asymptotic expansion of the oscillatory integrals, you have to use resolution of singularities. Okay, so this is the first thing that I want to discuss. So in a couple of minutes, I want to discuss a little bit about local zeta functions again. Okay, so probably the first zeta function was the gamma function. This is well known for those of you who are teaching calculus, or well, maybe you remember this from a long time. So this is probably the first zeta function, of course. Nobody call it like that, but it has the same properties. We can show that this function converges absolutely on this region, and moreover, it has an analytic continuation. And the proof goes very much the same like this proof that I make with the integrals. And we can prove that they have poles in the non-positive integers. Okay. So a little bit of history. Archimedean local zeta functions were introduced by Gelfand and Shiloh in the 50s in the book Generalized Functions. Generalized functions are known nowadays like as distributions. So in the ICM of 1954, Gelfand conjectures that the local zeta functions admit a meromorphic continuation to the whole complex plane. And one interesting thing is that the main motivation of Gelfand behind this problem was that the meromorphic continuation of these guys implies the existence of fundamental solutions for differential operator with constant coefficients. You can see part of this history in one of the books that are recommended to attend these seminars. So, as I showed you before, one solution to this problem was proposed by Besson in Gelfand and Ipentlanti by Atiyah by using resolution of singularities. This is the problem that we were discussing at the beginning. But then in 1972, Bertson gave another solution, saying a little bit more, and related this zeta function with something that is, I guess, well known for this audience. There are the roots of the Bertson-Sato polynomial. So what Bertson proved is that the poles of the local zeta function are integer chiefs of the roots of the Bertson-Sato polynomial of f. So this is the general strategy of the resolution of singularities proof. I'm not going to into that details because I'm more interested in other things. But the idea is to use the resolution of singularities, the map pi as a change of variables, and then we need to use a partition of the unity to localize the integral in every chart. And what happens is that when you use resolution of singularity, what we have in every chart is that the function is a monomial, and again, the pullback of the differential form, this is the top differential form, is monomial. And once you know the description of the poles of the monomial set of functions, then you're done. Okay. So this is the general strategy, as I was saying. But the big problem here is to determine the true poles, because any of these strategies gives just a list of candidate poles. Okay, and the challenge is to determine the true poles of this local zeta function. These are related with so many things, with monodromy zeta functions, with the monodromy conjectures, and other things that I'm not going to discuss here because I just want to concentrate on the properties of the local zeta functions. And I think that I'm going to stop here and let the space for some questions because it's time. It's okay?
Thank you so much, Edwin. Are there any questions?
Actually, could ask some very naive questions.
Sure.
So is it possible to explain? I didn't quite understand, for example, where did powers of logarithms come from in the asymptotic expansion?
Yeah, well, the thing is that there is a technicality there, and because the Fourier transform, what we are doing behind the curtains is using some properties of Fourier analysis. The thing is that the Fourier transform of distribution, like the monomial one, contains a logarithm. So in this change, but going from the integral in the integral inside when you use the Gelfand-Leray form and using the asymptotics when t goes to 0 and traducing this to the asymptotics when the parameter tau goes to infinity in the other side, what we are using is some properties of the Fourier transform. And the thing is that the Fourier transform of a monomial distribution contains a logarithm. Is like a monomial times a logarithm. So is where these things comes from.
Okay, thank you.
Any other questions? Okay, if not, then thanks again, Edwin, so much. And we will be back next week at the same time for some more.
Okay, thank you.